Welcome back to JVM Internals Crashcasts. I'm Sheila, and with me, as always, is our JVM guru, Victor. Today, we're wrapping up our season on JVM expert topics with a deep dive into performance considerations for JVM languages. Victor, are you ready to geek out about some benchmarks?
Absolutely, Sheila. I've got my stopwatch ready and my CPU cool. Let's dive into the fascinating world of JVM language performance.
Before we start, listeners, just a quick reminder that this episode builds on our previous discussions about Kotlin, Scala, Clojure, and language interoperability on the JVM. If you haven't caught those episodes yet, you might want to give them a quick listen first. Now let's kick things off with a quiz question to get our brains warmed up. Victor, here's one for our listeners. True or false? All JVM languages have identical performance characteristics once compiled to bytecode. What do you think, Victor?
Ooh, that's a tricky one, Sheila. It's tempting to think that once everything's compiled down to bytecode, it would all run the same way. But there's more to it than that. Without giving away the answer, I'd say listeners should think about things like language features, compilation strategies, and runtime behaviors. It's definitely a question that gets to the heart of our topic today.
Great point, Victor. Listeners, keep that question in mind as we explore JVM language performance. Now, let's start with the basics. Victor, can you give us a high-level overview of how performance might differ between Java and other JVM languages?
Certainly, Sheila. At a high level, performance differences between Java and other JVM languages can stem from several factors. First, there's the compilation strategy. Java is typically compiled ahead of time, AOT, to bytecode, while some languages like Groovy can be interpreted or used just in time, JIT compilation. Then there's the language features themselves. For example, Scala's extensive use of traits or Kotlin's null safety features can impact performance. Lastly, there's runtime behavior, including things like how the language interacts with the garbage collector.
That's a great overview, Victor. So, if I understand correctly, even though all these languages end up as bytecode, the path they take to get there and how they behave once they're running can lead to performance differences. Is that right?
Exactly right, Sheila. And it's important to note that these differences can manifest in various ways. Startup time, runtime performance, memory usage, and even how well the code can be optimized by the JIT compiler.
Interesting. Let's dig a bit deeper into compilation strategies. You mentioned AOT and JIT compilation. Can you explain how these different approaches affect performance?
Of course, AOT compilation, which Java primarily uses, compiles the entire program to bytecode before it runs. This can lead to faster startup times because the JVM doesn't need to compile code on the fly. On the other hand, JIT compilation, used by languages like Groovy or for dynamic parts of Scala, compiles code at runtime. This can lead to slower startup times, but allows for more optimized code based on runtime information. Some languages, like Kotlin, use a hybrid approach. They compile most code AOT, but can use JIT for certain language features. This tries to balance the benefits of both approaches.
That's fascinating, Victor. It sounds like there's a trade-off between startup time and runtime performance. Are there any real-world examples where this difference is particularly noticeable?
Absolutely, Sheila. A great example is in microservices or serverless environments. In these scenarios, applications need to start up quickly and might only run for a short time. Java's AOT compilation can be advantageous here. On the flip side, long-running applications like web servers might benefit more from the runtime optimizations of JIT compilation. For instance, Kotlin has gained popularity in Android development, partly because its hybrid approach works well with Android's constraints and performance needs.
That makes a lot of sense. Now, you also mentioned memory management and garbage collection. How do different JVM languages impact these areas?
Great question, Sheila. Memory management and garbage collection are critical for performance, and different JVM languages can have varying impacts here. Java, being the language the JVM was originally designed for, generally has the most predictable and well-optimized memory behavior. Other languages might introduce additional overhead. For example, Scala's extensive use of immutable data structures can lead to more object creation, potentially increasing garbage collection frequency. Clojure, with its persistent data structures, has a unique memory profile that can be very efficient for certain use cases, but might require tuning for others. Kotlin, with its null safety features, can reduce the occurrence of null pointer exceptions, but at the cost of some additional memory usage for nullable types.
Wow, it sounds like each language has its own memory fingerprint. Is there a way developers can optimize for these differences?
Absolutely, Sheila. The key is understanding your language's specific behaviors and optimizing accordingly. For Scala, you might focus on reducing unnecessary object creation. With Clojure, understanding how to effectively use its persistent data structures is crucial. For Kotlin, leveraging its inline functions can help reduce overhead. But remember, premature optimization is the root of all evil. It's important to profile your application and identify actual bottlenecks before diving into language-specific optimizations.
That's great advice, Victor. Now let's talk about some common misconceptions. What are some performance myths about JVM languages that developers should be aware of?
Oh, there are plenty, Sheila. One common myth is that Java is always faster than other JVM languages. While Java often has a performance edge due to its mature optimizations, modern versions of Kotlin or Scala can be just as fast and sometimes faster, especially when leveraging language-specific features effectively. Another myth is that dynamic languages like Groovy are always slow. While they can have more overhead, JIT compilation can make dynamic languages surprisingly performant in long-running applications. Lastly, there's the idea that more concise code is always faster. While languages like Scala or Kotlin can lead to more concise code, this doesn't necessarily translate to better performance. Sometimes, more verbose Java code can be easier for the JVM to optimize.
Those are really interesting points, Victor. It seems like performance is much more nuanced than many developers might assume. Before we wrap up, can you share some best practices for optimizing performance across JVM languages?
Certainly, Sheila. First and foremost, measure, don't guess. Use profiling tools to identify real bottlenecks in your application. Second, understand your language's strengths and weaknesses. Use Kotlin's inline functions, Scala's lazy evaluations, or Clojure's persistent data structures where they make sense. Third, don't forget about the fundamentals. Efficient algorithms and data structures are crucial, regardless of the language you're using. Finally, stay up to date with your language and JVM versions. Each new release often brings performance improvements and new optimization techniques.
Thank you, Victor. Those are excellent tips. Now, I think it's time to reveal the answer to our quiz question. The statement was, all JVM languages have identical performance characteristics once compiled to bytecode. Victor, what's the verdict?
The answer is false, Sheila. As we've discussed, even though all JVM languages compile to bytecode, factors like compilation strategies, language features, and runtime behaviors can lead to significant performance differences. It's a complex landscape, but that's what makes it so interesting.
Indeed it does, Victor. To wrap up, let's summarize the key points we've covered today. 1. JVM language performance differs due to compilation strategies, language features, and runtime behaviors. 2. There's often a trade-off between startup time and runtime performance. 3. Memory management and garbage collection behaviors vary between languages. 4. Language-specific optimizations can significantly impact performance. 5. It's crucial to measure performance and avoid premature optimization. Victor, any final thoughts as we conclude this season on JVM expert topics?
It's been an incredible journey through the depths of the JVM, Sheila. I hope our listeners have gained a deeper appreciation for the complexity and elegance of the Java virtual machine. Remember, whether you're writing in Java, Kotlin, Scala, or any other JVM language, understanding these internal mechanics can help you write more efficient, performant code. Keep exploring, keep learning, and most importantly, keep enjoying the fascinating world of JVM development.
Wonderfully said, Victor. And that brings us to the end of our JVM expert season. Next season, we'll be venturing beyond expert into advanced topics and future directions for the JVM. We'll be kicking things off with a deep dive into JVM security, so don't miss it. Listeners, if you've enjoyed this season, please subscribe to JVM Internals Crashcasts and leave us a rating. Your support helps us continue bringing you in-depth explorations of the Java virtual machine. Until next time, happy coding.